Well, maybe while we're waiting for this first slide, I'll just introduce myself briefly. So, as mentioned, I'm the head of R&D for natural language processing at CloudMinds. CloudMinds is an early stage stealth startup. This is somebody else's slides, although they look very interesting. They are not mine. CloudMinds has been around for just about a year. We were started by an entrepreneur named Bill Huang, who may be known to many of you, who also had founded UT Starcom. Bill is quite a visionary, not only in robotics, but also has a particular genius for making money and raising capital, and so that's our current reason for existence. Again, this is the wrong slide. May I have the correct slide, please? So this is not my talk. I'm sure it was very interesting, or will be interesting when given by somebody who actually knows what's behind it. Well, I'll do my best to just speak extemporaneously, trying to remember what all my slides were. So I have a particular thesis that I want to offer to this group. In robotics, as well as many other areas of artificial intelligence, the hot topic has been machine learning. Machine learning has had phenomenal advances in so many areas. We hear every day about Google or Facebook or many others developing new advances in deep learning and neural networks especially. The challenge is, do we actually know what the problem is we're trying to solve? The problems have changed in artificial intelligence. The problems that we're focusing on have changed as the technologies have changed. That doesn't mean necessarily that the technologies that were offered years ago are not or could not be successful. Something that the problems that people are tackling now are best solved by a particular set of tools. So I want to plant an idea that there are some other problems out there, problems beyond pattern matching, beyond sensing, beyond reaction. The things that numeric-based processing systems have done very well on are primarily pattern matching based, I would assert. And yet human cognition is much broader than that. We deliberate, we think about things, we reason, we plan into the future. We understand language in a way that is not simply reacting to the inputs given us, but which trigger a long chain of different sorts of processing in the human brain. By working on these different problems, I think we will find that we're going to need many different kinds of technologies, in particular symbolic technologies, in particular semantics, and what used to be called knowledge representation. So if we could move on to the next slide, please. So somehow we've arrived at slide 5. Could I ask that we back up maybe to slide 1, and then we'll go to slide 2? Okay, great. That was slide 1. Great. Slide 2 is after this. Thank you. So just in terms of my background, I've been doing knowledge-based systems for about 30 years, a lot of work for DARPA, some work on my own, and primarily my work has been centered around this notion of symbolic reasoning, of using logic, using mathematical logic. Mathematical logic is a topic in artificial intelligence that was really at the start of the field. It has had some great success, especially in the period of the 1980s where expert systems were popular. And then there was a sense, I'm afraid, as there is with any technology, there's a period of excitement, of hype, of overpromising, and then a sort of hangover that happens after that. And I want to try to wake us up from that hangover that has occurred and help us remember that there was this technology once that at one time was actually very successful. So let's move on to slide 3, please. So here is my thesis. I feel like sometimes I am the guy in the crowd holding up this big sign saying logic while everybody else around me is talking about machine learning. Now I'm stating this point controversially, right? If I said nothing shocking in this talk, it would be very boring at the end of a long day. It's already almost 5 o'clock. People are thinking about going home. How can I wake you up? By saying something that is shocking, that is controversial, but ultimately, I hope, actually true. That not only do we have machine learning, but symbolic systems are a good idea. So let's move on to the next slide. So we've presented this briefly already, thanks to our interesting slide presentation. So don't forget about knowledge-based methods. So next slide, please. So let's take a particular example in natural language. And I also want to draw a contrast with methods such as semantic networks. We've heard probably a lot about Google's knowledge graph. Facebook also has a knowledge graph. Knowledge graphs are wonderful things. People can understand them. They're very pretty. People love graphs. The problem is graphs have some real problems for knowledge representation. They have problems with context. And so let me give you an example of some context that actually matters. So imagine you have two sentences that are inputs to your robotic system, your robotic natural language understanding system, the sort of system that we're building at CloudMinds, as well as many others that people are trying to build. So imagine we have John thinks Anna walked to the store, and also separately, Anna is a doctor. Now, knowledge isn't going to be very useful unless we combine references to multiple things in the real world. Right? We want to know that Anna is this same person, that she has identity. We want to remember who Anna is, and we want to remember some things about her. But how do we do that in a way that's reasonable from the perspective of robotic memory? If we turn this into a graph, we have a nice graph that unifies around Anna. Look at this graph and just try to read through it yourself and think, what does it tell you? Okay, John thinks Anna walked to the store, so that's kind of the left-hand side of this graph. And Anna is a doctor. That's kind of the right lower side of the graph, but all linked through Anna. She's the same person. These things are both true about her. But the problem is when you come back to this graph, how do you know what was true? How do you know what the context was true? And graphs have this irreducible problem. Now, if you love graphs, and maybe you've done some work in semantic networks, maybe you use the OWL representation language if you're a techie like me, if you've done that and you feel comfortable with this, and you're wondering what I'm talking about and it's not hitting home, let's talk later, right? Because this is not a question of aesthetics or preference. It is actually a question strictly of mathematics, of being able to reconstruct the information that was in the original utterance from this kind of representation. If you try to read this graph and figure out what was true without knowing those input sentences, just from this abstraction, you'll get the wrong answer. Now, that's a problem. Right? If your robot gets the wrong answer, if it doesn't know the difference between John thinks Anna is a doctor and Anne is a doctor, and yet you could reach that conclusion by looking at this graph. So hopefully I've planted a sort of seed of doubt in your minds that will help you be motivated to look further and understand how do we represent knowledge? How do we represent it in graphs? How do we represent this knowledge in networks for learning graphs of relatedness from our machine learning algorithms? How do we store that information? How do we store it so that it is truth-preserving, as a logician would say, so that any operations we do on it are guaranteed to continue to be true and not come up with false conclusions? We wouldn't want false conclusions. All right? Next slide, please. So what's the answer? So let me present the answer. Now, normally I give a 14-week university course in ontology, and so I'm just going to throw some code at you and understand that I don't expect you to necessarily be able to read it. I hope it will pique your interest. If it just piques one person's interest at this whole conference that then digs deep into this science, I will have achieved my role here. I have made this day worthwhile, for myself at least. So the thing that we should be doing is formal logic. So some of you might have had, in fact, I hope all of you had at least an introduction to mathematical logic in college. Right? At least any computer science here probably had an intro to logic where you learned about predicate calculus. And you probably learned lots of examples of, Socrates is a man, all men are mortal, therefore Socrates is mortal. Simple deductions, simple facts, and how we deal with that in logic in a correct way. So logics have gotten really sophisticated now. We can say all sorts of things, and we can say all sorts of things in a very formal, mathematically provable way. But we can also say it in a very efficient way. Right? So it doesn't have to be slow. There's been tremendous advances in theorem proving to make this stuff fast, to make it practical. It is not just the realm of science and academia, but there's still a sense that it is, because 10 years ago it was slow. 10 years ago it was obscure, but thanks in large part to a lot of scientists in Europe, this technology has continued advancing. And now my sense is, and in the work that I'm doing with the team that I'm building to do natural language processing at CloudMinds, I'm convinced that we need both technologies. We need a strict, formal way of stating what we know about the world. Somebody earlier today, I think a lady from IBM who gave a wonderful talk, also said something that I wanted to argue with a little bit. She said 80% of what we know is uncertain. The last time somebody asked me, isn't everything we know uncertain? I looked at him and said, are you a human? Many things we know are absolutely certain. We shouldn't have our machines have to learn everything from scratch every time, and with a confidence value. There are things that we know in this world that are absolutely true, and if we're careful and we're good scientists and we pick the right way to write about these things, we can record them, and we don't have to learn them each time. We can learn them once, and we can reuse them. We can reuse them year after year, and that's what I've spent my career doing, the last decade and a half, of recording all this information about the world in logic, by hand, one statement at a time. So now that the robots have this compendium of world knowledge that they can reason from, so they can be intelligent, so they can not just react to the world in simple programmed ways that they learn, but that they can deliberate, that they can understand the depths of natural language, not just what to say next, but the 100 or 1,000 things that are true and follow from the things that they have been told. So one more slide. I think that, in fact, may be the end. Is that the last slide? Yes, one more slide? Or a blank page to show me that, in fact, we're at the end? Okay, that is the end. So thank you very much for listening. I would love to talk with you further about this stuff.
为了感谢一直以来Pease 先生对我们的支持，我们现在请李强先生给他颁一个我们的奖牌。Okay, now I would like to invite Mr. Qiang Li to give a present token of appreciation. So please come to the center of our stage.